Okay, guys, picking up where we left yesterday, I started just briefly talking about example 4, which is based on example 3. So we've got it all here together. Example 4 wants us to consider the function instead of from 0 to x, from 3 to x. And so they changed it from g to f. I skipped over a for the moment because I wanted to talk about b. And I'll go back and get a in a moment. But b asks us, what is g of 0? And so g of 0, I had us plug in 0 as we were getting ready to leave, yes? So we plugged in 0, and we have the integral from 3 to 0 of f of t dt. And I can't remember if this is the first place I introduced it or if I'd introduced it earlier in the lesson. But the idea, we don't usually have integrals go from 3 to 0, do we? So in order to have that integral flip, one of the properties we're going to learn, and I think it comes up in lesson 6.4 as an official property, one of the properties we're going to learn is that you can flip the values on the integral and that by putting a negative out front. Okay? And so the negative integral from 0 to 3, well, if you go back up here, we did the integral from 0 to 3 and got 4.5, right? And so with that in mind, this is a negative of it, so g of 0 is negative 4.5. Now, what I wanted to connect here, or one thing to connect, is that over here, f of 0 was 0, yes? Now we're at g of 0. G of 0 is negative 4.5. So that's saying when we go to graph this here in a bit, that point is going to be down there 4.5 units lower. Okay? And again, part of the doing, we're trying to make the connection here. Now, if we back up to A, my brain wasn't in the right spot yesterday. I didn't have the easy way to teach A in my brain. It all of a sudden clicked. So, it says, what is the 0? And so, when we talk 0, we want to know where does it cross the x-axis, right? And where does it cross the x-axis means when is your y value 0? When is this integral going to equal 0? How does the integral equal 0? When the lower and upper limit are equal, the same, right? We talked about that a couple of times yesterday. And so if my lower limit is 3, when my upper limit is 3, this integral will equal 0, right? Because if you're going from 3 to 3, there's nothing to take the area of there, so that's a 0. And so what is the 0 of g? And that is 3. And I put x equals 3. Now, with that in mind, think about that ordered pair. That ordered pair would be 3, 0. And if we graph that, here's my 0 of my next graph. Well, what do you notice about that point from the previous graph? It's down 4.5 units, isn't it? Okay. So, noticing some of these connections here. Domain of G. What's my domain of G going to be? Is it going to be any different than my domain of F? No. It's still going to be, you're still technically, and I don't have a chart to fill out here, but you're still using the same initial graph, and so that domain is still going to be 0 to 10. I don't think I found the values here, did I? No. Thoughts on the total change in G? And I know we haven't filled in the values yet.
We're saying it's the same as it was up top.
Same as it was up top? What have we noted so far? These two values both move down 4.5, right? If everything moves down 4.5, there's still going to be the same net change, isn't there? Okay, it's going to be at different values, but there's still going to be the next change, or same total change, excuse me. So yes, total change is still going to be 6. And I feel like it'd just be easier to sketch the graph here, and then we'll Yeah, let's go ahead and sketch the graph before we finish answering these. So easiest thing to do, take each point and move it down 4.5. So at 0, 0, we're now at 0, negative 4.5. It was right one up a half. Move that down 4.5 and you're at negative 4. It was 2, 2. So now it's going to be 2 and I'm going to be down 2.5 if I'm doing my math correctly. We already have 3, 0. Let's see, it was at 4, 8. So if we move that down 4.5, we're going to be at 3.5. It was at 5, 11. So if we move that down 4.5, we're now at 6.5. It was 6, 12. If we move that down 4.5, we're at 7.5. 8, 9. Move that down and you're at 4.5. And 10, 6 is going to move down. And that's going to be at 1.5. Same curve, just translated down 4.5 units. So what is the max value of G?
7.
7.5. Where will it occur? Still at x equals 6. What's the range of G? Okay, negative 4.5, less than or equal to y, less than or equal to 7.5. Okay. The connection, okay, if you think back here, let's examine what would happen if we allow k to take on different values. Here k was 0, here k was 3. Notice when k was 0, my ordered pair at 3 was 3, 4.5. What did we do here when k became 3? Well, now we moved the graph down 4.5. So there's that connection right there because we changed to 3. That translated my graph. Okay. I think. Oh, we technically do still have IJK, which I just gave some of that information up then. Okay, well, I just prepped you for IJK, which are on the next page. I thought it was a different problem. Okay. I don't know if you can read that or not, but hopefully you can. Describe the relationship between f of x equals the integral from k to x of f of t dt as k takes on different values. Well, I kind of just gave that away. I was thinking we didn't have to write it down. Okay. What's happening? Depending on the value of k will determine a shift, a vertical shift, vertical translation. Okay, so all f of x functions would be vertical, did I say shifts, translations? I have vertical shifts here, either way. So all f of x are vertical shifts of each other. What point must lie on the graph of any given family member and why? If you go back I'm trying to think how I want to explain this. What do you notice about A here? When we put 3 in, we get 0, yes? Okay. What is 3 in this case? 3 is also the given K value, if you will, right? Well, what was K up here? K up here was 0, right? What did you notice here? When that K value is 0, you get 0. Okay. So the point here, we had a point that was 0, 0. Here we have a point that was 3, 0. In both cases, the X value is the same as the K value. Okay. So the idea, because if you put in X to be whatever K is, what's always going to happen here? If your lower and upper bounds are the same, you're always going to have a result of 0, because the area from something to itself doesn't exist. And so the idea here is then what point must always lie on the graph? And I'm going to call that K comma 0, because whatever you can always put in, whatever the matching K is, and it will always give you 0. So the idea, how do I want to say this? When the lower bound equals K, then you have the integral from K to K of f of t dt, and that will always equal 0 there. When upper and lower are the same, that's always going to equal 0. Actually, I should say the area is that integral. Okay. And then part K. Again, I kind of already gave this away. As K takes on different values, the function's graph, okay, the English on this is weird. As K takes on different values, the functions f of x equals the integral from K to x of f of t dt graph as blank transformations of one another. What type of transformations did we talk about? So it's vertical shifts, vertical translations. So vertical transformations of one another, each containing the particular point. What did we just talk about? We're always going to have that point K comma 0. Even though the lower bound changed, is f prime of x equal to f of t. And what we need to talk about, have we talked about this? Have we not? I feel like maybe I've talked about this. So the idea you guys know the basics of math. When you do something on one side of the equation, you do something to the other side, right? So if I take the derivative of f of x, that becomes f prime of x. Now, if we take the derivative of an integral, well, I've already thrown the word out there. We haven't really used it yet, but I've thrown the word out there. Then integral is taking the antiderivative. And I've talked about how the fact that an antiderivative is going the opposite way of a derivative, yes? So if I say that, what are a derivative and an antiderivative going to do to each other? A derivative and antiderivative are going to undo each other, cancel each other. And so if we undo, what happens if we cancel this integral? What's left? It's just, instead of doing the integral of f of t, it is just f of t. And again, that's on the newer end, I know. But when you take the derivative, and I could write this, well, I don't know if I want to do that yet. Because I could say, if you recall us writing like d of dt or d of dx, where we take the derivative of something, I could write it like that. Okay? But the idea that a derivative will undo an integral, because it's undoing the antiderivative. So notice what it says here. The derivative of capital F is equal to regular f here, or f of t. So even though the lower bound change is f prime of x equal to ft, yes, that will always be equal there. Okay? Okay. Questions on that section? I think I got everything there. Okay. Let's look at example 5, which I have on the next page. We get some cool colors. Sorry, it was too expensive to have ours colored, copied in color. So I looked into it, but I couldn't justify the cost. Shown below is the graph of the derivative f of some function f. Assume f of -3 equals -8. Okay, so they're already telling us that. Now, we need to find, I'm trying to think where I want to go with this. Okay, the first question they ask us to find is f of 2. And okay. The idea of this problem is they're giving us an initial condition. Okay, or initial condition, or if you will, an initial value. How that initial value changes things up is, instead of us just having the provided areas, we know at -3, what do we know at -3? F of -3 is equal to -8. Everything adds or subtracts from that. Now, if you think logically, if we go to the right, what are we going to do as we go to the right? You are going to be adding values. What do you think we're going to do as we go to the left? You're going to be subtracting values. So the idea is that we're starting with the fact here that capital F of -3 is equal to the value of -8. Everything's going to build from that. Okay?
The y value.
What?
The y value is -8?
Yes. Yeah.
So
At an input of -3, the output is -8. Okay? And I mean, here's the deal. We don't have a function describing this here. Okay? We're going solely based off of the initial value. Now, with that in mind, and I guess what I want to say is, okay, so when we say f of 2, think of this as going, I want to say that or not. I mean, there's a way in my brain that my brain is saying, okay, we're going from -3 to 2 here. When it says f of 2, I don't have a function right here, do I know? So it's saying, okay, we're going to, basically you're finding the area from -3 to 2, but what is our starting value? Our starting value is -8. And then you're going to add or subtract those pieces on appropriately. So we're starting here at f of -3 is -8. This one's f of 2, so we're going over to 2 here. So with the fact that f of -3 is -8, and then accumulating up to 2. So what do we have to add on if we're accumulating up to 2?
36.
Yeah, we have to add on the 10 and the 26. And realize that 26 is for the whole red area up here. I got a little confused on that on my own at one point. So, because we're going right, we're adding. So I'm going to write it as 10 plus 26, or as Miles said, 36. And we end up with 28. Okay, so we're working with how do we work with this initial condition or initial value. Okay, try the next one. F of 6. So again, in a way, you're thinking, okay, we're going to go from the initial value of -3 up to 6. Okay, thoughts? Almost.
28 minus 8.
Okay. So what do we know about this 8 since it's below the x-axis? It's a negative, yes? We talked about that yesterday. So that's a negative. Now, why did she say 28? Basically, she was looking at 2. We're already at 28, aren't we? And so the shortcut is to say, okay, I'm at 28, and then I'm going to subtract 8 because it's below the x-axis and add 14. I know if you look at my notes, I have -8 plus 10 plus 26 minus 8 plus 14. In other words, I wrote out all the pieces. But what do we end up with? 34? What about f of -5? F of -3 equals -8, and then what? What am I doing with the 18? I'm subtracting 18 because I'm going left. Okay? Just like typical math, you go left, you subtract, you go down, you subtract. You go right, you add, you go up, you add. -8 minus 18 is -26, I believe. Okay, did we catch on there? I know it's a little different, but okay. D. Since the area under F is positive on the interval from -3 to -1, we know that the graph of F must be blank on the interval -3 to -1. Okay, so note the difference here. The area under little f is positive on this interval. So what is going on with the graph of f? Think back to what we know positive tells us. When we think about first derivative. If the first derivative is positive, what's it tell us the main graph is doing? Increasing. Okay, and that's the connection we're trying to draw here. You can use this idea here too, that this is going to apply in all these scenarios, that derivative of big F is equal to little f. You can use that idea as well. Okay. Since the area under F accumulates at an increasing rate, so we're talking little f, increasing rate, we know that the graph of f must be blank on the interval -3 to -1. So notice it didn't just say increasing, it's increasing rate. So now we're going more and talking more about second derivative. And that's going to tell us what? What?
Concavity.
Concavity. And since this is an increasing rate, we are talking about being concave up. Because remember, a second derivative is derivative of the derivative, right? So it's the rate of a rate. So here it's an increasing rate. The area under F on negative 1 to 2 accumulates at a, what did I say? Negative 1 to 2. So this area is accumulating from negative 1 to 2. What's it doing this time? From negative 3 to negative 1, it was accumulating and increasing. Here, this time it is decreasing. So it's accumulating at a decreasing rate. So F must be what on that interval then? Capital F, that is. It would have to be concave down on that interval. Now, G asks us to sketch a graph. We just have one graph here, so it doesn't specify color. Show the extrema, inflection points, and horizontal tangents. I don't think I showed quite all of that on my graph now that I think about it. There's some stuff we can talk about, but I didn't show all of that. Okay, so let's see. What did we have? At negative 5, we had a value of negative 26. We had that, right? At negative 3, that was our initial value of negative 8. At negative 1, we didn't do negative 1. Negative 1 would have been, you start at negative 8, you add 10. So we're at 2. Let's see, we didn't do f of 2 either, did we? Oh, that's A. I didn't even look at it. So that's 28. There we go. Don't mind me. What about f of 4? No, we did f of 6. Gosh, it's 34. What's f of 4? It's going to be the 28 minus the 8, so 20. Okay, so sketch those values there. Not going to be precise, obviously. Negative 5, negative 26. Negative 3, negative 8. Negative 1, 2. 228. 420. 6. 34. So if we connect these pieces, redo. Okay, I really don't like how I did that, but we'll go with it. Good enough. This is a graph of capital F, so this is y equals capital F of x. Okay. There's some extrema, yes. And I think we'll just talk about it here. But there's some extrema. If this graph only goes from negative 5 to 6, we have a absolute min here. Absolute max here, so my endpoints would be my min and max. Absolute, those y's. We also have a relative max, relative min. Those all would be extrema, right? Inflection points. You would have some inflection points when concavity changes, right? For instance, there's going to be a concavity inflection point somewhere here, because somewhere in this area my concavity is going to change from being concave down to concave up. The rest of this graph, I'll tell you, my graph doesn't even look identical to what I drew in my notes. So, you know, if you get one little point a little bit different, it doesn't look quite the same. So, Because it changes, yeah. Because we change concavity, so yeah, that one would be. We didn't talk about anything over here, but so I'm assuming Jacob's pointing out based here. I'm not sure. It looks like a concave inflection point on mine, but maybe, kind of. So I didn't get anything written down in mine, so I don't know why, but I skipped over that part, I guess. Okay. One more piece. That is example 6. In differential calculus, we use the derivative f prime to discuss properties of a function f. In integral calculus, we need to reverse our thinking. So this is the whole relating positive to increasing, negative to decreasing, all that. Our new goal is to use derivative functions to talk about antiderivatives. In the example below, we say that g is an antiderivative of f. Summarize relationships here. So instead of using capital F, this is using g. So g of x is the integral of f of t dt, basically, or is equivalent to it. You can also, if you use the thought of what I said earlier, the derivative of g, actually I'm not even going to put the x there, but the derivative of g, well, when you undo this, when you take the derivative of the antiderivative and undo it, that's going to equal f of t there. Maybe I will put the x's and t's in there. But the idea that the derivative of g will actually equal f there. Now, what we have graphed here is it's labeled as a graph of f. Okay, so f is positive on this interval. Pretty obvious there, right? F is positive on the interval 0 to 8. So g is what on this interval? And again, this is using the idea that g is an antiderivative of f. Well, what do we know? When something's positive, then it is increasing. Excuse me. Oh, this is where I don't like how this graph is done. Because we're talking, well, f changes signs where? Yeah, it says 0 and 8. But I'm just going to use 8 here because we can't really do both at the same time. Because okay, so it changes signs, right? Here it changes from negative to positive. Here it changes from positive to negative. For whatever reason, the answer key only put 8 in there. Which, true, it does change signs at x equal 8. I'm not going to disagree with 0 because I see it. So, g must have a relative what since f goes from blank to blank? There's going to be a relative maximum. Since f goes from positive to negative. That's old news, right? Okay. The graph of g is decreasing where f is blank for values of blank. Well, where's the graph going to be decreasing? When f is, where's decreasing happening? What? Okay, so less than 0. I wrote negative. I was expecting to hear the word negative. That's why I was like, wait, what'd she say? Okay, so a graph is decreasing where the original is negative for values of, when is this happening? When x is past 8. for when x is greater than 8. The graph of f is increasing on what interval? 0 to 4 is what I'm looking on because it's the graph of f here. And they just have increasing 0 to 4. Again, I don't know. I feel like it was never defined. I feel like, I guess we're not going before 0, I guess, is what we're talking about. So I'm not sure why that's there. But so the graph is increasing from 0 to 4. So I wrote it as 0 less than x less than 4. In my notes I have equal to. Do I need equal to? Okay. If the graph of f is increasing, what do we know about g then? And this is going to that second derivative step. If the graph of f is increasing from 0 to 4, then g is going to be not just positive, but think concavity here. Concave up. Okay. And then the graph of g is concave down, where f is decreasing. For values, where are we decreasing? X past 4. So x greater than 4. And the graph of f has a maximum value at x equals 4. So g has a, what did my graph do at 4? It changed from, it changed concavity there. It changed, here was concave up from 0 to 4. Here it's decreasing, it's concave down after 4, so it is an inflection point. And I'm going to have to come up with some better ways to relate that all, I think. I'm going to have to work on that. Because I don't have the best tools in my toolbox to relate that right now, I know. So, yeah.
Why do we think second derivative? Or on D, I'm sorry. D.
Okay, sorry. How do I want to answer that? I guess good question. How do I answer that? It's a valid question. I'm not discounting it. How do I want to answer that? They talk about shoes again. Okay. I don't have a good answer for you right now. I know, bad to say. I'm just being honest here. How do I want to answer that? How do I want?
Would it be because, like, when you think of the derivative when it's increasing, you think that the derivative of that is positive?
But isn't G just the? I guess I'm not sure.
And this is where what I was saying just a little bit ago about you need to come up with better ways to, like, this is one of those things I'm realizing that it's in my mind, but how to get it to you guys, I'm struggling with a little bit.
So G stands for the derivative of G of X.
Well, officially what we have to think about is g is the antiderivative of f. Now, also trying to connect that, okay, this graph is f, so this graph is also the derivative of g, if you want to think of it that way. I'm going to have to work on my connection here. How do I get this? Yeah, let me sit down and think about this. Because I'm struggling right now with how fully to connect it. Okay. Now, I will say this is a page at the bottom that has a chart at the bottom, right? And it will help to connect some of that stuff. So, I guess, did I put this on another screen? Okay, I did. So, when the derivative function f, and it talks about each of those pieces, the antiderivative, so notice here, antiderivative, talking about g. So here we're looking at when f is this, and g is this. Kind of the same idea as, first derivative and original function. So the whole positive causes increase, negative is decreasing. When we had an increasing first derivative, or I don't want to say it. When the second derivative was increasing, it caused the function to be concave up. Decreasing caused concave down. It's the same idea there. When something changes the signs, those are our mins, maxes, our zeros, so to speak. Okay? Let me work on how I need to connect this better. And in order to do that, I'm going to have to sit down and get my head straight first. Okay? Because it's not clicking right now in my head. Now, with that said, for the most part, you should still be pretty good with homework. Because I think most of this, and I will say the homework is, sorry, it's not just a 2-page homework this time. I think we're back to 4 pages. I know, it was so nice to have the nice short one the other day, wasn't it? So,
I didn't do that on purpose.
go through this and I will figure out what I want to do to connect better. Okay, so go through the homework. Answer key should be available online. Go through it tomorrow. Come back with questions, okay?